I'm Curtis Ballard. I am your track lead for the AI presentations that will be held in this room. If everything is going swimmingly, encourage you to thank Jason Mulligard and Brooke Candelaria and Mike and all the other folks that made things come together. If there's any issues with the way things are going in the AI track, please contact me and let me know if you've got any feedback about the way things are going, suggestions on topics for next year, etc. Got a lot of great topics for you today. Hope you'll stick around and be able to join us for the topics all week. We've got an entire 3 days of topics related to AI, storing data, transporting data, using data to accelerate your AI processes. I'd like to thank all the great speakers that will be presenting later this week. As I mentioned, I'm Curtis Ballard. I'm with the SNIA Technical Council. At the conference today, this presentation is sponsored by the SNIA Technical Council. We want to put together some material to try and kind of give everybody a little bit of an overview of some of the ways that AI uses storage and help create some foundational information for the conversations that will be coming up later this week. Most of the conversations we'll have later this week are going to be a lot deeper in depth on specific parts of the AI workflow. So this presentation builds on a couple I've done earlier. They're linked at the bottom of the page there. They're quick 30-minute sessions if you're looking for just a really speed overview. This, like I said, is a high-level overview of the use of storage in AI processes. And we're trying to have this be some thinking food to get you thinking about the big picture, how everything all fits together, and be able to position the talks that are going to come later today for how they fit into that bigger picture of everything all together. So I've been asked before, when you give this talk that's an overview on storage for AI, what kind of storage are you talking about? Are you talking about file storage? Are you talking about object storage? Are you talking about block storage? Is this direct attached storage, NVMe SSDs, in your AI server? Are these external, fabric attached, SAN attached storage devices? I put down the answer here. It depends. This presentation covers the generalization of the AI workloads and from a perspective of storage. And the specific storage for any given phase of your AI workload can change depending on your specific needs and the phase of the workload you're in. But as I've gone through this a few times, I've had consistent feedback that rather than it depends, the answer to what kind of storage should be yes. If you really are optimizing your AI workload for the best possible performance through the whole pipeline, you will find that different types of storage fit in different places. And if not in your AI workload, in your neighbor's AI workload, just about every kind of storage you can imagine will fit and will accelerate the way things work. As we talk about AI, everybody focuses on AI from the, talking about the training and the inference and the cool things that AI is doing for us. We don't always stop and think about what does AI run on? What is the fuel for AI? The E in your electric vehicle or the gas in your gas vehicle if you're of the previous generation. It's the data. The data behind your AI is really the foundation of your AI, what makes everything valuable, and taking care of that data, refining that data, getting that data into your system is essential for having a good AI pipeline. So remember that while we talk about CPUs and GPUs and every kind of XPU that you can think of these days as people make accelerated processors, they all run on data. And that data is getting bigger all the time. Here's an example of some of the types of AI through the years, where we started out with some of the traditional AI pieces, neural networks 30 years ago, using a few megabytes to a few gigabytes of data, all the way up to, we're talking 60, 80 petabytes of data these days for some of our generative AI processes. And what we don't stop and think about all the time is that is only the training data that we're talking about there. I've seen the industry shift a little bit over the last year, and there's a little bit more thinking about the big picture beyond just training. But a lot of the material that you're going to run across focuses on AI training large language models, and the data sets for the training those large language models. A lot of us aren't training the large language models. A lot of us are. Some of us, that's our only job. But a lot of us are using those large language models, and the whole rest of the pipeline is critical for what we need to do with AI. So what makes AI really interesting from a storage perspective? I've been in this industry for over 30 years now. Probably shouldn't admit that, but I have. And the AI is really kind of fascinating. It really is kind of the first time that the workload in every environment that is running AI, the workload is really variable and really affects how your systems run. And you have many customers that have similar workloads, different but similar. They're doing similar phases of AI. They're using similar tools. Where it used to be that you could learn one customer's workload, and that was unique to that one customer. Now the workloads are getting a lot more interesting in many respects because you can have some predictable workloads. You can optimize storage for specific parts of it. And in the AI processing, you're working with huge amounts of data, scale way beyond what a lot of us had worked with previously. Most of my career, we worked with little islands of data that were doing different things scattered all over people's enterprises, data centers, businesses. Now people are pulling together everything, wanting to have one view of all of their data. So you're working with huge amounts of data. You're doing extensive data manipulation, where you used to just do a few queries and read some key parameters out of the data. Now you're doing extensive actual manipulation of that data. You've got a multi-phase workload. We'll talk about that more as we come along. And the different phase workload does different things. There's wildly variable performance and capacity for different parts of your AI pipeline. And you've got highly parallel operations in some places. All of this produces a very interesting workload at the storage through different phases. So we're going to take a look here at a quick intro to the use of storage by AI. There's really two sides to AI where most of the focus is, where most people are making their money building things. You got training and you got inference. So on the left-hand side of the model here, we always tend to do left comes first, right comes second in the US, so stuck with that. On the left, we've got our model training. You've got some form of unstructured data, comes into some sort of funnel, goes into an engine, and you get this miraculous trained model comes out. Then you've got continuous loops going back over to your inferencing. The inferencing side, you're dropping in some sort of production data. In the middle, you've got that trained model that we created on the left-hand side. And out the bottom, you want to dump a cargo ship full of business value. And you tie those two together in a continuous feedback loop, updating the model into your inferencing, taking the results of your inferencing, feeding that information back into your model training to make your model better, and over and over and over. A virtuous cycle, we sometimes call that. But there's always a but, and we put a but in this case too, because we've got to have one. And if you want to get the big picture, we have to remember there's a bunch of different phases of the process that support these two key sides of AI. And every one of those phases uses storage differently. To really understand the big picture, you want to be thinking about all of those phases and how they're using AI. So let's take a quick look at what does an AI pipeline look like. Now, this is going to be from a storage perspective. Most presentations that you'll probably see tend to be coming from a compute perspective or from a GPU perspective. And some of the phases that I'm going to break out here get gathered up into one. But this is kind of how I've broken it up as a simplified view of the data processing phases for AI. And I'll try and use this diagram as we go through the presentation to kind of give you an idea where we are talking about things. Super simplified here. You got your data ingest comes in, you go into data cleaning, it goes into data preparation to model training, model eval tuning. You magically create a trained model to run inference on. And then over on the right-hand side, you've got your data archive. We'll look at this further as we go along. Done variations of this talk for a few times, and as it's been pointed out to me, the world's really not that simple. It really looks more like this, and even this is going to be wrong for some portion of installations. No one diagram can capture everything. But you got all kinds of data running around. You got your production data, you got your training data, you got your inference data, you got your tuning data, you got your production feedback, and you got your trained model. Everything running around through your network, hooking up to stuff. All of these lines are places where data is used in one phase and needs to be used in the next phase. That line may be a data movement. That line may be a changing the pointers of your data, but data feeds from space to space to space. And the same data gets used in various different forms over and over and over. And next year, this diagram will probably change. Anybody got any complaints? Let me know. Be happy to refine the diagram. But we'll use the simplified diagram for most of the stuff we talk about today. So I wanted to take a little bit of a look into the overview of the data processing phases for AI and try and think a little bit about what happens in these phases. What might the storage workload look like? Now, I was talking to somebody last night. I was telling them, I've tried to simplify things in this presentation, get you thinking about how things work, move things up a level. Some of this stuff, has to be simplified to the point that it's overly simple. Kind of the only way you can try and get a grasp on AI, I think, is you have to oversimplify it. So I've tried to simplify this stuff as much as I can and think about a little bit of the concepts behind what's going on here, how are things working. So let's start out. We're going to be off in this phase up here. I call it the data aggregation phase. In my little diagram, I've got a funnel there that's got the training data pulling into it. In this data aggregation phase, in my simplified model, I'm showing the training data going into there. In the real world, we're finding that more and more your production data goes into some similar pipelines. But again, we're going to have to simplify things to keep this high level. So in the data aggregation phase, it's critical to remember that good AI results requires good data. If you don't have the data, you can't get the answers. You have to store all of the data that you're going to need to get the maximum value out of your AI processes. What data is that? That is a hard challenge. I've met companies that say, well, it's just too hard to figure out what data is valuable. I'm going to store everything. If you can do that, that's fabulous. Some companies can just store everything. And please do that. My company sells storage. But realistically, most of us can't store everything. Talk to a customer that's in a industry where they're running refineries that have millions of sensors throughout the refinery sensing everything that's going on, and they're sampling thousands of times a second. You can't keep all that data. So you have to stop and think about what is your environment. What data do you need? You have to identify the data and the data sources. Today, it is almost always some form of multimodal data, documents, log files, text files of various kinds. Increasingly, pictures are factoring in, photographs of various different spots through the production lines. I've seen, X-rays of circuit boards are some of the data that people putting into pipelines like this. You get video. If you got a manufacturing line, video of your manufacturing line just running might be feeding into your system. You can imagine that turns into a huge amount of data quickly. All of this has to go into your data aggregation phase. So you have to carefully consider where your business information is, what sources of data are going to most likely have those valuable pieces that you're going to need later. And so you're going to have to feed it into some sort of a data ingest phase with your ETL processes with connectors to the right data pipelines to get that identified data into your transformed and loaded into your data lake. We usually call this phase. And then there's going to be some cleaning and pre-processing. I've put cleaning and pre-processing in the data ingest phase. I think that that's what most of us are going to end up having to do. You have to take some of the data as it's flowing in, and you're going to have to filter and throw away some of it. At least some of the cleaning is going to have to be done. You're going to have to detect and remove duplicates. So you're going to have to look for outliers that might skew your results. That sometimes they're valuable. You might need to move them, not throw them away. But you have to look for that. You have to do things like look for incomplete data that has to be either removed or repaired. And you have to normalize your data. Lots of things that we didn't used to do before. The incomplete data, I think, is really interesting. I saw one AI evaluation where people were trying to work on some data, and they discovered that they had no idea that they had huge numbers of records in their system that they were capturing that was incomplete. One field wouldn't get filled in on lots of data, and you get bad results. So you got to think about making your data clean. So what does the workload look like here? So you thought about what's happening. How does that turn into a storage workload? Your data ingest patterns are going to vary. They're going to vary. Just about everybody's got a different ingest pattern, and you have to think about what your data ingest pattern looks like. Most customers I've talked to, there tends to be some form of continuous data generation. Sometimes it's continuous at a specific frequency, easily serialized. Sometimes it's bursty with certain processes generating lots of data and other processes not generating so much. Most of the time in the ingest phase, even data that seems random, you can figure out a way that you can serialize the data and you can feed it into a data pipeline that's optimized for taking in serialized sequential data, get it laid out in an optimum manner for your storage efficiency. Capacity-wise, we often call this a data lake these days. You want to have a lot of capacity. Storing the right thing takes lots of capacity. Like I've said earlier, information that you don't have can't be recaptured. If you've lost that data, you can't get it back. So you want your capacity to be kind of as large as you can afford. What do the data access patterns themselves look like? For the writes, we talked about that. The data ingest is writes. Hopefully you can sequentialize that. Reads tend to be fairly random as you're going around doing cleanup of your data. And then you do some random writes of the clean data back into the system. So you tend to have a high sequential load of everything coming in with random reads and writes for the data cleaning phase. So what do you want for performance? This is one of those cases where you tend to want your performance to be as fast as affordable at the right capacity. So you have to trade off all of your different aspects there. If you can get the right performance, you can do more with your data ingest storage. If you have to have capacity and give up performance, that may mean copying data out of your ingest storage into a less expensive, higher performance storage for your next phases. And in this case, I think it's kind of interesting. I've seen a couple of examples of both extremes of the case. Last year I talked a little bit more in detail about a customer that had their ingest, their data lake coming in, was all high-performance flash storage, enterprise-grade storage, and they loved the performance until they started running AI, and they just filled up their storage instantly. They had too expensive, too high-performance storage. Seeing probably a little bit more the other end, where people had very low-cost storage for capturing their data lakes, but then they discovered that they didn't have the right random read-write performance to do some of the data cleaning and data prep phases. So think about your data ingest to make sure you get the right storage there. So we've got the data, we've got it cleaned up. Now we have to go into data preparation. We have to turn the data into AI food, I call it. This is a phase where you're going to have your data scientists are going to have to work as translators to figure out what's the data that you've got, how does that get turned into AI food. Data scientists are expensive. This is a phase where everybody that I've talked to is trying to automate it. Have their data scientists figure out where the most valuable data is, and then figure out how to automate grabbing that data out rather than have your data scientists do the data extraction all the time. So they have to explore the data, they have to identify patterns, they have to identify some of the outliers we talked about earlier, figure out relationships to the data. These data scientists are highly valuable people, and because they have to have domain-specific knowledge and figure out how to get the right information out of your data. Have to do things like splitting it for training and testing, have to do what we call feature extraction, which converts the features into consumable nuggets, numbers that the system can process. Most of it ends up being turning into a data transform phase, converting your data into data types that your AI engine can consume. We call this vectorizing. You take your information, you convert it into a numerical nugget that is kind of a word, shall we say, for the AI to consume a word. There's just a few bytes that identifies the data. We call that a token, and then you run the tokens through a process that embeds them with information so that your specific AI model can process that. We call that embedding or vectorizing, creating vectors that have a lot more information around them. So every word in your system turns into a much larger byte of data that we call vector. This is often highly parallel, and like I said earlier, you have to have some domain knowledge. So this data ingest, the data ingest here is the data that came out of your aggregation phase. So this is one of the places where I said you might be able to use a single storage environment. I've had people ask me after the talk, so as you talk about a bunch of different phases of storage, says, how many different storage systems is that? Well, that's another case where the answer might be yes. Ideally, you think about things holistically and you figure out ways to move your data as little as possible. But do usually end up having to have multiple different types of storage with different performance characteristics and move your data between them. Ideally, your data ingest and your data preparation can run out of the same storage pool. The data access patterns are different when you're doing the data preparation, though. Data preparation takes less capacity than your data ingest because you're not working with all the data, you're working with the cleaned data. And your data access patterns here are very random read-write. Over here on the left, you'll see as we go through these, I tried to put in some little diagrams to give just kind of a general perspective of what you might see here. Sequential to random. In this phase, you're going to be highly random read-write. Your write performance is going to need to be good. Your read performance is going to need to be good. So then we get into model training. There's tons of presentations about model training. I swore I wasn't going to go very deep into model training. It's so interesting. Couldn't help myself. And there's a little bit more here than I meant to have. But again, you kind of got to have a feel for what's going on in the model training to understand what storage you need behind it. There's a lot of phases of the model training that are running in GPUs, some in CPUs, using dynamic memory, RAM, HBM, and they're not accessing your persistent storage, but the persistent storage is still a critical process that's backing your model training and affects how well your model training is going to run. You're going to have to load the memory for training is one of the key places that interacts with storage, where you have the case that you may have some highly specialized small models where you load the whole thing into the GPU memory and then you just run. In the early days of AI, I remember people saying, you really don't need the storage. You load everything into the GPU memory, you just run out of GPU memory. we've figured out how to make models that don't come close to fitting in GPU memory. So your storage is becoming, external storage is becoming increasingly important as you have to load those models into GPU memory. And you usually have to do that several times over the course of training. The model needs to periodically go back, or the GPUs need to be reloaded with new pieces of the model. The other thing that's important, and we focused on a lot earlier, is checkpointing. During the model training phase, there's a process called checkpointing. We'll talk a little bit more about later. That is creating a point-in-time copy of the model, and with large models that have long running durations, you want to be able to checkpoint and restore. Any of you that worked in the HPC space where you had long-running things like simulations, been doing checkpointing for a long time. That's become way more critical as we go into AI training and have things that can run for months at a time. You don't want to restart. And all of this is usually multi-GPU concurrency. So you got lots of GPUs running in parallel, doing everything we talked about, thousands of times in parallel beside each other. So let's talk a little bit more about what those things look like. The data loading for your model training. Your data has to be formatted properly to match the GPU. There's a lot of tools that do that. Some of the popular tools are tools like PyTorch and TensorFlow can get your data formatted into the right format to match your GPU. There's also GPU vendors that have tools that can get your data formatted in the right mode. So this it has to read from the storage, run through CPU, get the data formatted right to go into the GPU. Then you have to format the data the right way for your GPU training. I can't even begin to touch on that. I had some slides on it and decided to scratch them out. There are several different types of parallelism where models are broken up different ways and loaded into the GPUs for training. And so your data will end up getting broke up and spread around the GPUs. You'll have many worker threads loading the GPUs in parallel. And if you want to learn more about it, there's a really good SNIA webinar, and there's other webinars around, but I linked to one of the SNIA webinars there. And for loading this data into the GPU, there's lots of different processes, and people are inventing new things every day. Originally, it was traditional CPU driven. The CPU reads data into memory and pushes over into the GPU. Quickly moved into RDMA accelerated with the data being coordinated by a CPU but being loaded directly into GPU memory over an RDMA link. There's a lot of talk these days about GPU initiated, where the GPUs are actually sending the read-write commands down to the storage. And I put a hyperlink there to what I think is one of the seminal papers in that space that is a BAM system architecture, they call it. And some of the people, I'm sure you know some of the authors on that paper, found that really interesting paper on GPU-initiated storage. So the checkpointing phase. This is constantly evolving. The first time I gave this talk, I prepared a slide on checkpointing. The first piece of feedback I got was, hey, your checkpointing slide was about 4 to 6 months old. We've come up with new things. And this one is probably 4 to 6 months old too. But it's certainly updated from the last version. Checkpointing is work that has to be done, but it's not generating you money, so everybody works on efficiency, making it as efficient as possible. Often there is some GPU stall time during your checkpointing, and you don't want those GPUs stalled any more than necessary. So there's lots of different models for doing checkpointing. I see there's a session tomorrow that's talking completely about checkpointing, so I'll be interested to see what the latest is they're presenting there. The storage performance tends to drive the checkpointing frequency. The more frequent checkpoints reduce the cost of restart, but they come with the penalty of having a little bit more GPU stall time as you create your checkpoints. There's really two primary methods. We started out with synchronous checkpointing, where you copied the GPU memory to CPU memory and then wrote it to a SSD, with your GPU stalled while you were doing that. That quickly was replaced with what we call async, where you do your state copy to the CPU memory, send your GPUs off running again, and in the background you take periodic snaps of the memory and copy some of those out to persistent storage. So during model training, you got your data work loading phase runs. You need your performance to be just maxed out on your read performance to get the data loaded into the GPUs. That often includes some CPU time to do some pre-processing with some data transforms. Lots of parallel threads doing read-write processes for the next training batch. Traditionally usually been filed, but high-performance object is really gaining a lot of interest. I'll be interested to see where that goes. It's often random samples, but each tends to be read sequentially. So depending on where you're looking at it, it can look like random reads, it can look like sequential reads. I think that it tends to be randomly reading sequential pieces, and depending on the performance of your storage, you might be able to get some sequential performance benefits out of the sequentiality if you can understand how that happens. Checkpointing, you get your files written sequentially. Usually, I say maybe multiple sequential writes in parallel. I think you're seeing that it's almost always multiple sequential writes in parallel now. During restore, it is definitely sequential reads in parallel, and you really need to have the performance fast so you can get those reads out, get your system running again when you have to recover from checkpointing. A few other thoughts about model training. Just couldn't help myself. There's so many cool things to think about here. A fast object for AI. I think this is really interesting. I'm one of those people that in the early days, I looked at, everybody was doing file access for their AI training, and object is too slow, and I looked at it and I thought, my goodness, you look at the overhead for object is always going to be too slow. Maybe not. People are clever. There's new things being invented every day. While file has been the most popular, fast object seems to really be gaining interest. It's usually SSD, virtually always SSD. And we're seeing RDMA accelerated fast object. There's some talks this week about RDMA accelerated fast object storage with an SDC session. I think that's a little bit later today. And then there's a BOF. I think my slide's out of date. My slide says the BOF's Tuesday, but I'm pretty sure that BOF is this evening now. Apologize for that. So there's an SDC session and a BOF both on fast object for AI. Should be really interesting. Some thoughts on model training, general storage planning. Won't spend much time on this slide. I've used this one in previous sessions. You can go get more information from those. Things really are still true. The GPUs drive the cost, so you want to maximize the use of the GPUs to optimize your investment. If you consider the data sources, if you know your workloads, you may be able to optimize your storage to match the workloads that you're expecting for this specific AI session. There's what I think is a good webinar that was done at SNIA, probably getting a little bit due for a refresh, but it's still got a lot of good information about ways you can kind of do some calculations to figure out the types of performance you need for your storage for a given training workload. So after that detour, as I got distracted a little bit by training, let's get back to looking at our workflows here. So after you've done the training, you have to do model evaluation and tuning. This is often considered to be part of the training. Most things that I've looked at, training and the model evaluation and tuning are completely inseparable. The storage characteristics, the workload you see at the storage, though, are different when in the model evaluation tuning phase from the training phase. So I broke it out as its own separate phase up here over towards the right. You have to successfully be refining your training with new data. That data may be understanding the results of your training from the last run, tuning things to get a little bit different behavior. It may be that you have new data that you want to feed into your training process. There's a lot of different goals for why you want to tune your AI models, what you're evaluating for. Sometimes it's improving accuracy. In the early days, the stuff I looked at was all about accuracy, accuracy, accuracy. But there's Other types of tuning that are needed too. We've heard a lot about tuning to remove bias, to balance things out. Frequently when you find that you've got bias in your AI model, that you need to augment your data, get some more data that balances out the training data. You might be tuning for a specific focus, for a highly tuned model for specific use cases. But whatever you're trying to do, you have to apply various different techniques to tune the model. I don't have time to go into any of those at all today. The kind of the two key types of things that people end up doing is doing some adjust to your tuning parameters, doing things like noting new data, and then retrain the entire model. That's what we did in the early days. More and more, you're fine-tuning specific layers of the model. So you take, inject tuning into just part of the model and rerun just part of the process. A lot more efficient that way. And you're constantly evaluating how the model results match your expectations, so you can figure out how to tune it. A bunch of different techniques there. I can't go into hardly at all. So the workload during this phase, it's very much random reads for evaluating your model. You have to evaluate your results against your data sets. Usually you want to have test data sets and validation data sets. You have to run it against your metrics. Very, very much a random read load. Updating the hyperparameters in some sort of structured format like JSON or YAML, that's very much random reads and writes. Reading in hyperparameters, adjusting your hyperparameters. Usually pretty low capacity requirements. The tuning isn't a huge amount of data in terms of your overall data pipeline. But in terms of performance, you want that read performance maxed out. You want to be tuning, evaluating and tuning and feeding it back just as fast as you possibly can. And again, like I said, mostly random. So let's get into some of the fun stuff. Spent most of my time already, and I haven't even got to why we're here. I think we're seeing the industry shift this last year to inference is where you generate your value. We spend a ton of time collecting the data, training the models, et cetera. What we really want to do is we want to do some inference to generate some business value. Unless we're one of those lucky people that trains models and sells models, the inference is where the business value is at. That is the process where you take your AI model and you use it to infer information based on your inputs and what the model's been trained to give you a learned result. The really super simple abstraction here, I've had a lot of people ask me, how does AI do this? My summary is that these trained models, what we're doing during this training is you're training pattern recognition techniques. You show them patterns over and over and over, data in and results, and your AI models tend to generate a pattern recognition so that they can make conclusions from the data. The last time I saw this data with this type of a pattern, here's the next thing that came along. So they use those learned patterns and techniques to manipulate the data, doing what they've seen before, and they can generate recommendations. Now, storage access patterns for inference vary a lot, but there are some themes. So I tried to put in here a quick intro to inference. I can just barely scratch the surface, but I tried to scratch it at least a little bit to get you thinking about this. We start out with simple inference. Your input prompt is tokenized, you convert it to numbers, you feed the tokens into a neural network, you perform computations on those tokens using just the training and information in your selected AI model. The knowledge that you're using is all embedded in your model using the training weights, and you generate some output tokens. And your results are stored with random writes. We came up with this thing called a context that tracks information from where you are in your session. So a context allows you to retain some information before and run some more. Example storage size, a GP3 context window was 2,048 tokens. And now we've got GPT-5 that if they advertise can support 400,000 tokens. I think it's, 272,000 tokens input and 118 or 128 on the read. But from 2,000 in GPT-3 to tens of thousands to hundreds of thousands of tokens stored for context these days. Now, in simple inference, the first few phases are mostly using memory. They can all be done in the system, in your GPUs, CPUs, without hitting your storage, your external storage again. So then you've got the results stored in random writes and the context that gets written to the external storage. Most of your inferences move significantly beyond this. So the thing that most people, that you'll hear about the most these days is we took that simple inference and we've moved to RAG, retrieval augmented generation. One of the things we quickly learned with the simple inference is you train your model with all this data, and as soon as you're done, even really before you're done, when you've locked in your data, your data is getting old, and it just gets older and older and older. So very quickly, this technique RAG was invented that has really made AI way more valuable. RAG retrieves additional information from some associated databases to extend the knowledge of your AI model. Now, it requires some data prep that's a lot like the data prep that we talked about earlier. You have to take all your augmented data, you have to vectorize that, you have to put it into a vector database, and that generates a large storage data set, again, that you have to use. So now storage gets more exciting during the inference because all of your augmented data. During the RAG process, the prompt that you put in is used to query your vector database to retrieve additional information to augment the knowledge in the model. And then the additional information, along with your prompts, are all fed into the model to generate more up-to-date information. And after the step of running through, everything gets stored into your context window. The newer models, context window is just growing and growing and growing and growing. You'll hear some in several other talks today about KV cache is one of the popular ways to store those context windows. And so the amount of data that is written for each phase of that is just continuously growing. And then you have situations where you've got interactive sessions. A person's working with your AI engine, generates some information, and then walks away to have lunch. You want to store that off to persistent storage. You can't afford to keep it in memory. So your external storage gets used more and more. And that's just scratching the surface. There's many more models of inference. There's thought models, chain of thought, tree of thought, graph of thought. There's multi-agent models where you query a whole bunch of different AI agents and then combine everything and look at it again. There's a mechanism called reinforcement learning where you inject information to help reinforce correct answers. We're seeing deep memory models or long-term memory models now where they retain more and more context information about what's happened in the past to make better recommendations. I think it's interesting that every other kind of inference you can come up with, every time I read about a new inference technique, 2/3 of the way through, halfway through, I run into, and we're going to put RAG with it. So it's good to know about the RAG because you use that technique with just about every kind of inference you can come up with. There's RAG plus knowledge graphs, RAG plus reinforcement learning. I threw in here RAG with the kitchen sink. For those of you in the US, the kitchen sink's a metaphor for everything you can think of. So it's good to understand the basic concepts of RAG, and then there's all kinds of other inference. So what does the workload for inference look like? Like I said, it's got some variations, and it depends on the type of inference you're doing, but it tends to be random with more reads than writes. The read workload is usually lots of random reads. You read the input prompts, and you read the augmentation data for the RAG. So the augmentation data for the RAG is going to be reading, most cases these days, it seems like everybody's going to vector databases. So there's a specific workload around vector databases that you can understand and tune your storage for to make your RAG processes fast. And there's reading your saved context to start up the system when you're resuming a previous session. The write workload tends to be saving your output and saving your context. The saving your context, the hot thing these days seems to be the KV cache, as I talked about. There's some sessions later this week that talk about KV cache. Saving your output, you've generated video, you've generated pictures, you've generated documents. I'm not an artist, don't consider myself artsy at all. I don't draw pictures, I don't draw diagrams much. Since AI came along, I find I'm generating way more graphics than I used to, and throwing your ideas at an AI engine saying, hey, generate me a graphic with this. So I'm filling up my storage with stuff that I didn't used to create. And I've kind of got a soft spot in my heart for this phase. And as an industry, I feel like we're not really thinking about this one at all. It's not the glamorous, it's not the expensive, but we really don't want to forget our archives. In the capacity pool there, I blew my model. Instead of having a single circle that's full for your capacity, the capacity for the types of archives that we're going to need for the data that we're using and generating with AI is just exploding. A lot of our current storage mechanisms that we're using, we can't affordably store the data we're generating. I think we're going to have some really interesting work figuring out how to address what we do with all of our archival data from our AI processes. It's important to know some of this is mandated by regulations. There's some EU regulations on things like self-driving cars and storing the data that you use to train and storing some of the data that you use for driving. There's all sorts of reasoning models now where the model is instructed to explain the different steps that it goes through. And in some places, you're supposed to be archiving all of that information about what the model did to get to these different steps. So it's generating tons of data. It's similar to some of our traditional archives, but I say it's not quite the same thing. One thing that I think is really different with the archival that we're using with some of our AI processes, there's a lot more thinking about reading your archive back. A lot of our historical archive has been put it in cold storage and hope we never read it back. A lot of the archive that I'm seeing people trying to build for AI, they're wanting to bring some of the data back. Sometimes they're wanting to defrost large amounts of data and drop it back into the system. They may take a data lake and train a model and then put that whole data lake into an archive, and then 5 years later or 6 months later, they've come up with new algorithms and they want to rehydrate the entire thing and retrain. I think there's no accepted terminology for this type of archiving yet. We'll get to come up with a term for it. As engineers, we'll probably give it some really cryptic term that nobody understands. But I've heard some use of the terminology cold storage. Don't know that that's really gaining traction, but and this data set is just growing and growing and growing every day. Every time you tell an AI engine to generate a meme that you can send to a friend or generate a PowerPoint slide that you're going to present to an exec, there's more data that somebody's going to put in an archive somewhere. And we really need to think about low-cost, low-carbon footprint storage to do that. There's a couple of spaces that SNIA has been dabbling in around DNA and optical that I think are kind of interesting there. Nothing clearly is really broken through there yet as what is this next generation archival storage. With that, I thank you for attending. Apologize, I didn't leave a lot of time for questions, but I probably could maybe take one question if somebody has a question they'd like to ask. Yes.
So you mentioned this is primarily file and maybe object if it's performant enough. Why not block?
Well, good question. I didn't touch on that a lot, but like I said at the start, the answer to what type of storage is yes. The file and object reference that I've made was primarily during the training phase. That most of the training phase is reading pieces of data that tends to be read from files and objects. Block storage gets used extensively in some of the things like the data lake that may be object storage. Frequently there's some block storage behind it. Some of the things with KV cache, some of the KV cache stuff is very much looking at using block storage. So, great question. There's been a lot of focus on file and object being used in AI, but a lot of that's in the training phase, data lake phase, and your block performance and high-performance block storage is still important. Okay, with that, I do need to stop, respect other folks' time, so thank you very much. I will be around all week. If you have any other questions about my seminar,